Welcome back, everyone. Houston Math Prep here to talk about the fundamental theorem of calculus. We're going to talk about a couple ways in which derivatives and antiderivatives are related to one another. So when we approximate area under a curve, we use what's called a Riemann sum. Sometimes you use a left-hand sum, a right-hand sum. You might use a midpoint sum. If we look here at this expression, remember that n is the number of rectangles that we're using to approximate. And we've said that the more rectangles we use, the better the approximation is going to be. Our formula for the area of each rectangle, remember, is going to be the height times the width. Our function value at some x is going to be the height on that interval, and then we also have delta x, which is our width of each rectangle. So this is the width times the height here, and we're summing up a certain number of rectangles to approximate the area. For a Riemann sum, if we take more and more rectangles, we get a better and better approximation of the area under the function. So how could we get the most accurate approximation, or how could we get the exact area under the curve? The idea is to just let our number of rectangles approach infinity. The idea is that each rectangle would get skinnier and skinnier. We would pack more and more rectangles into this area we're trying to approximate, and so the number of rectangles would approach an infinite value. We're going to go ahead and focus on this formula of taking the sum of n rectangles with the formula f of x times some delta x. If you think back to derivatives and you think of the mean value theorem, that said if your function was continuous on some closed interval a to b, and also between a and b it was differentiable, then we said you could find some slope of a tangent line that was equal to the slope of the secant line, and this is what the mean value theorem said was guaranteed to happen as long as our conditions were satisfied. If we just do some rearranging of this formula, we multiply both sides by the denominator b minus a, we'll get f prime of c times that quantity b minus a is equal to our numerator f of b minus f of a. And then if you think about taking the antiderivative of both sides, keep in mind this b minus a is just some constant. So I'll end up with not the derivative of f, but f of c times b minus a equals the antiderivative at b minus the antiderivative at a. If we call the width of this interval b minus a, we just call it delta x, and then we get an expression that starts to look very much like the Riemann sum that we were just looking at on the left-hand side here of my equation. So I'm going to take that, put it down in the corner here just to remind us, and then we'll look at this formula we had inside of our limit as n approaches infinity before. So when we have this sum of n rectangles, we have this formula, think about what delta x really is. That's the width of each rectangle, right? And this delta x is going to be the x value on the right side of the rectangle minus the x value on the left side of the rectangle. That will give us the distance across the rectangle, the width. So we'll just call that our right side x value minus our left side x value. That's the same as our delta x here. And that'll be true for each rectangle. So this is the formula for each rectangle. And if we're using n rectangles here, let's go ahead and use this idea that f of c delta x is equal to capital F of b minus capital F of a. So if I start plugging in at 1 and I go to n, so think about plugging in 1 here, this would be x1 minus x0, and using this formula down here, that would give me capital F with x1 plugged in minus capital F with x0 plugged in. If I then plugged in k equals 2, I would get x2 minus x1, so we would get a similar expression, capital F of x2 minus capital F of x1. If we plugged in k equals 3, we would get the next one, etc. If we skip a bunch down to the very last one, which would be plugging in n, we would get x sub n minus x sub n minus 1. This list, you can see here, my subscript values are increasing one term to the next. I'm going to go ahead and turn this around backwards, this list. It's going to be useful for us to see it backwards, so we're going to put the last term in the front and the first term in the back, and so you can see our subscripts are now going down by 1 each time. But think about what's happening here. Notice my f of x1, I'm adding that, right? I have plus in front, but in the group before I have a minus f of x1. So that's really going to reduce what I have over here. You can see our f of x2, we have a minus f of x2 in front of it as well. So every positive term is being canceled out by the negative term before it. This f of x sub 3 is being reduced by the thing before it. You would have something right before this one that would be reducing there, right? So we're just going to get, really, the only things left that don't have something they reduce with are f of x sub n and the minus f of x sub 0 at the end. So we get that at the very end. But now when we do a Riemann sum, realize what this x sub 0 and x sub n are. What is your x sub 0 when you start doing a Riemann sum? Well, it's the very left endpoint, right? And this x sub n is on the right side, right? It deals with the very last rectangle, and so that deals with x equals b. So if you're approximating from x equals a to x equals b, these are actually b and a, right? So this is actually f of b minus f of a. And if we take this limit as n approaches infinity of this sum here, we think about taking an infinite number of rectangles, we know that that's supposed to give us the exact area underneath the curve, right? And we know the exact area underneath the curve is the same as the definite integral of our function of x dx. So this statement here tells us the exact area underneath f of x dx between the axis and the function on the interval x equals a to x equals b is simply going to be the antiderivative with the right endpoint plugged in minus the antiderivative with the left endpoint plugged in. And this is one of the statements of the Fundamental Theorem of Calculus, that the area under a curve on the interval a to b for x can be calculated using the antiderivative, plugging in b, then subtracting what you get when you plug in a. So let's look at another connection here between derivatives and antiderivatives. If I define some area function to be the antiderivative of f of t dt on the interval a to x, so the idea is we have the area under the curve here between some value and any x value, that is our area function, and we can define that by taking the antiderivative and plugging in x, and then subtracting what we get when we plug in a to the antiderivative. Now to bring in the derivative relationship here, let's imagine we took the derivative with respect to x of this area function. So what would happen if we took the derivative over here of capital F of x minus capital F of a? Well, this is the antiderivative of f of x. So if I took the derivative, I should get back f of x, right? That should be equal to f of x. But what is the derivative of this with respect to x? Well, if I've plugged in some constant, some a, then this would just be some number. We'd get minus some number. And we know the derivative of a constant is 0, right? So really, we just get back f of x when we take the derivative with respect to x of this integral, this definite integral, that is our area function here. Let's go ahead and work a couple of these, and then we'll establish a pattern of how these work. So we have the derivative with respect to x of the definite integral from 1 to x of sine of t dt, right? So these are t bounds because we're integrating with respect to t. So let's first go ahead and do our integral, and then we'll worry about the derivative part. So we'll go ahead and say the derivative with respect to x, we'll keep that out there. And now, what is this antiderivative? Well, when we take the antiderivative of sine of t, we actually get negative cosine of t. And we would evaluate from 1 to x, so we need to plug in x, and then we subtract what we get when we plug in 1, right? So that would give us the derivative with respect to x of, if I plug in x for t, I would get negative cosine of x, minus, if I plug in 1, I would get negative cosine of 1. We won't actually compute cosine of 1. Let's just go ahead and write down a slightly simpler way of writing this. So we'll say negative cosine x, that actually is plus cosine of 1, right? So you might be able to tell one of these is a function of x and one of them is a constant, right? So when I take the derivative with respect to x of this function of x, I should get something that is non-zero, right? So the derivative of negative cosine x is sine x. And what do we get when we take the derivative of cosine of 1? This is just some number, and the derivative of just some number is 0, right? So we actually get sine of x. So the derivative of this definite integral with sine of t in it, dt, taking the derivative with respect to x, we get sine of x. So you can see it looks very much like maybe we just replaced t with x, right? Let's try another and see what happens. So if we take the derivative with respect to x of the definite integral from 1 to x squared, let's say, a different bound here, sine of t dt. So the integral part will be the same, right? If we look at just doing this definite integral, what's the antiderivative of sine of t? Well, that would be negative cosine t again, of course. This time we'll be evaluating from 1 to x squared. So if we plug that in, think about what that's going to say. That will say the derivative with respect to x of negative cosine with x squared plugged in for t, so negative cosine of x squared, minus, again, we're getting negative cosine of just some number here, right? And that doesn't have to be 1, it could be something else. So now when we take the derivative, think about what's going to happen, right? If I take the derivative with respect to x of negative cosine of x squared plus cosine of 1, a similar thing happens, right? But now we want to be careful. We have a function inside of our cosine function. So just doing the outside part first, the derivative of negative cosine something is sine of that something. But then the chain rule says times the derivative of the inside will give us 2x there, right? Now the derivative of our next term, that's just a constant, that would be 0, right? So we do get something extra, right? We get 2x sine of x squared. So it turns out it's not just a replacement property here, right? If it were a replacement property, I just would have gotten sine of x squared, but I didn't. I got 2x sine of x squared. So let's figure out the general rule then. If we have this definite integral in terms of t and we take the derivative with respect to x, we know we get some replacement, but we get something extra, it seems like sometimes. So here I'm just putting some function of x as my top bound. I'm not specifying if it's x, x squared, x cubed, cosine of x, something strange up there. Could be lots of different things. So we're just going to say for any function as my upper bound, what happens? So we'll leave the derivative part in front and just do this antiderivative, right? So if we take the antiderivative of f of t, then that should give us capital F of t, right? That's what it should give us. We would plug in our bounds, so we would plug in a, that constant bound. We would plug in whatever function of x we have up here. And if we do that, then that tells us we would get the derivative with respect to x of, think about when we plug these in, right? We would get capital F with g of x plugged in, minus, and then we would get capital F with a plugged in. So now let's take the derivative with respect to x for this expression here. So if I take the derivative with respect to x of capital F of something, that should just give me f of that thing, right? So not touching the inside, I would just get f of g of x, leaving the inside alone. Now the chain rule says we then multiply by the derivative of what's inside, right? So we would get times whatever the derivative of the inside is, and that's the derivative of this first part. Minus, remember this is just a constant, so the derivative of this constant would be 0, and so this is what we get, right? So it looks like we do get replacement, right? I am just putting g of x into whatever function is in here, right? So it is a replacement theorem, but we need to remember that with derivatives, the chain rule is certainly going to give us times g prime of x, right? The chain rule is something we have for derivatives, but we don't really have a chain rule for antiderivatives. So using the idea that we know that this is then a replacement theorem with chain rule, we should just be able to evaluate this without having to do all of the stuff, right? So if I replace my t in my function of t with my bound function here, that would give me cosine of x cubed. That's the replacement part. But then if I use the chain rule idea and I multiply by the derivative of this bound here, this function of x, then that's going to give us times 3x squared. So we'll actually get 3x squared cosine of x cubed for this one. All right, everyone, those are the two parts of the fundamental theorem of calculus we wanted to go over. This idea of how derivatives and antiderivatives are related and how we can find the exact area underneath a curve on an interval just using the antiderivative of that function. Check out our videos coming up in our series where we actually calculate some areas underneath curves using definite integrals. Thanks for watching. We'll see you in the next video.